it's nice to see everybody online, and thanks for the invitation to come speak. Before I begin, I just wanted to take a moment to thank the many collaborators and students who are involved in all of this research. Obviously, science is not an individual endeavor, so I really need to acknowledge all of the great collaborators and students in my lab, as well as funding organizations. So as Joe mentioned, I do study lots of ways that climate change in particular is affecting lakes through ice changes, water temperatures, water quality, and changing fish distributions. But I think of all the topics that I study, ice is my absolute favorite. And there's many reasons, I think, for that. So first, ice is, I can't see the chat, so if anybody needs to talk to me, just feel free to unmute. But ice has been used by people for centuries. Back in the day, ice was used for refrigeration, to keep our food cold. Ice festivals are really common in Canada and around the world. So some of the largest ice festivals are actually in China, where 25 million people might attend these ice festivals every winter. Recreation, skating, ice hockey, a big part of northern cultures, as well as and ice roads that connect remote communities to one another. And because ice has been such an integral part of winter for northern communities, we have ice data collected long before the advent of meteorological stations. And so these time series are some of the longest collected directly by humans for ecological data, but also climatic data. And some of our longest time series actually come from spiritual organizations. So, for example, this bust here of John the Evangelist is carried between a church in Switzerland and a church in Germany as a sign of friendship between the two countries. And this ice record in Lake Constance goes back to 875, but the lake hasn't frozen since 1963. I'm going to talk about this record a bit more. This is a record going back to 1443, collected by Shinto priests. There's lots of citizen scientist groups that also collect ice records. So I've recently inherited a citizen science project, community science project, with over 1,000 lakes across the US, and different people measure ice in different ways. This is Lake Simcoe, just north of Toronto. And it's a men's group that puts a truck onto the lake with a timer. And then when the truck sinks, that's their ice off date. And this record goes back to the 1850s. And some of our best records actually come from gambling pools, which is kind of interesting because there's just so many people watching the ice breakup for that lake or river. So for example, the Torn River data set goes back to 1693, and we have such detailed records of when exactly the ice started to break up. The other great thing about working with ice is that it's a sensitive indicator of climate. So as you've learned in elementary school, water freezes when temperatures are below 0 degrees Celsius. And there's some wiggle room around that, depending upon the size of the lake and the lake characteristics. But lake ice is a sensitive indicator of climate. And as I mentioned before, weather stations existed. And so the timing of ice on in the fall gives you an idea of when winter air temperatures started to fall consistently below 0 degrees Celsius, and the timing of ice off also gives you an indication of how long that winter season was. And so then we can use this information to understand how climate change has affected lakes, and in some of our cases, long before the start of the Industrial Revolution. And the longest, most consistent lake ice record that I mentioned earlier is from Lake Suwa in Japan. And the reason is that there's a Shinto shrine on this lake. And 15 generations of Shinto priests have recorded the dates that the lake froze in diaries and on rice paper, etc. I've actually, yesterday was a soft premiere of a film that I'm an executive producer on Lake Suwa, and the filmmaker spoke to the priest, and he actually mentioned that they've been documenting this observation that I'm going to share in a few minutes for 20,000 years. It's just what we've been able to find written down extends back to 1443. And so what the Shinto priests were interested in was the date that the lake froze and the date that this ridge on the ice forms, the Amawatari. And the reason is because it goes back to their tradition and their religion. So the story is that there's a god and goddess that live together on the shores of Lake Suwa. And sometimes what happens when people live together for too long, they got into a disagreement and the goddess moved out. And she actually moved out and built herself a shrine on the other side of the lake. And every year when the lake freezes, the god crosses the frozen Lake Suwa with his dragon. So I was able to work with Japanese historians and linguists to sort of identify what this ridge represented, and it represents the footsteps of the god crossing the lake. And so every year when the Amawatari forms, the Shinto priests perform a purification ceremony. They bring together important leaders from the community, and they record the date that the lake froze, that the Amawatari formed, the shape and direction of the Amawatari, and they used it to forecast rice harvest. So early in the time series, when there was no Amawatari, it actually corresponded to widespread famine in the region. And what my collaborator, John Magnuson from the University of Wisconsin-Madison did was he learned of this data set and he went to visit the shrine in Japan. And he worked with the chief priest, Mr. Miyasaka, as well as a limnologist in the area, Tadashi Arai. And they translated these records on rice paper and just these records kept by the priests to Excel spreadsheets. So here you can see these Excel spreadsheets. And that's sort of where I came in. And I'm going to show you just some of the things that we've learned about ice from the Suwa record, as well as we have over 2,500 other long-term ice records now. So in the first 250 years of the ice record, so we've got time on the x-axis, years with no ice on the y-axis. In the first 250 years, the lake did not freeze 3 times. The next 250 years saw increased deforestation in the area, more people moving in, and the start of a revolution period, industrial revolution period in the region. And for example, from 1950 to 2000, the lake did not freeze 1 out of every 5 years. Since about 1988 to 2018, the lake did not freeze 8 out of every 10 years. And so what we have seen is just this dramatic shift to years with no ice. We've projected this into the future, and I'm just gonna this more. Okay, and we've projected this into the future using a whole suite of climate change models and scenarios, even very aggressive climate mitigation scenarios. And there wasn't one climate change model that forecasted the presence of ice after 2040. And so something, that's been maintained for 20,000 years, these ice observations are set to be lost within a few decades. And Lake Suwa is not the only lake that's starting to experience these ice-free years. We've started examining a variety of lakes that are experiencing these conditions, and you can see on the x-axis we've got winter air temperatures, and on the y-axis the percent of ice-free lakes. And as we approach this 0 degrees Celsius mark, you can see this rise in the increase in ice-free lakes. And we created some models to extrapolate how to predict which lakes are experiencing what we call intermittent ice covers. So these are lakes that used to freeze every winter, but in the last since the 1970s are starting to experience ice-free years. And you can see that we estimate about 15,000 lakes across the Northern Hemisphere that are experiencing these ice-free winters, typically in southern regions as well as coastal regions where winter air temperatures might be approaching 0 degrees Celsius. Here we worked with the New York Times actually to create this graphic for us, summarizing our projections of temperature of intermittent ice cover with temperature warming. And so you can see this northern shift of lakes that are experiencing these ice-free winters within this century. At the most extreme level, so recently we took this to the most extreme situation, and what we predicted, for example, in this figure, is that almost 5,700 lakes may lose ice cover permanently within this century. And again, these are lakes that are found in southern latitudes and along the coast. However, even moderate mitigations of greenhouse gas emissions really changes the picture, such that only 429 lakes may become permanently ice-free. And I'll talk about the ecological and societal implications of this a bit later. But mitigating greenhouse gas emissions is the primary factor to consider to preserve ice cover. Which lakes are most sensitive? Well, it's lakes that are found in southern and coastal regions where winter air temperatures are approaching 0 degrees Celsius. But also even in colder regions, deep lakes are really sensitive to losing ice and warming, because these large water bodies take longer to cool down in the fall, such that they're available, like the water temperatures are low enough to prime the lake to actually freeze. And if you've been keeping track of the Great Lakes ice coverage this winter, you've probably noticed that the lakes did not completely freeze over, and there's actually very little ice coverage in these large Great Lakes, whereas smaller ponds and smaller lakes have frozen. Even for lakes that still freeze, so there's a large millions of lakes that still freeze each winter. We're finding that ice is being lost at rapid rates. So what we did was a reanalysis of John Magnuson's science paper in 2000, and added some more long-term time series, and his data set ended in 1995. And so we added 25 more years of data of ice records, updated those ice records. All of our ice data is actually available open access at the National Snow and Ice Data Center, as well as through a recent publication in Scientific Data. But what we wanted to know was how are ice trends now with an additional 25 years data. What we found was that we have earlier ice breakup, but primarily there was a really rapid loss, rapid rates of delay in ice formation. So 11 days per century, to the point that we're seeing across these 60 lakes shorter ice duration by 18 days per century. What was most alarming was that in the past 25 years, rates of warming are 6 times faster. So actually, we had to double and triple check our calculations a few times because just ice duration was shorter by 108 days per century in the last 25-year period, faster than any of the other time periods that we've collected data for. So why? There's a whole slew of factors that contribute to shorter ice duration, but the most important factor, the factor that explains the most variation, are increases in air temperatures related to increases in CO2 emissions and greenhouse gas emissions. That explains the most variation in our ice records. Local weather, such as temperature, rainfall, snow cover, snow depth, wind, that solar radiation, those are important factors as well. And they can help predict within like a week to 2 week period when your lake ice may freeze or thaw. And then these large scale climate drivers, this is, back when I started this research, we had a lot of questions from climate skeptics about the role of solar sunspots and Milankovitch cycles that last 90 years on our climate. And because of these ice records that have such long time series, we can actually start understanding the role of these large-scale climate drivers. And they are important, but they don't explain that much variation. However, what we do notice, this is work from a graduate student, Leanna Lopez, in the lab, where she looked at ice breakup dates along the x-axis and these breakpoints in ice records where we saw an even further increase in acceleration in ice loss, and here specifically an earlier ice breakup date. And what she was able to identify were these like important large-scale climate drivers that contribute to changing temperatures. So, for example, there's a large El Nino Southern Oscillation pattern in the late 70s that has contributed to the acceleration of warming. In Scandinavia, the 1988 signal is quite strong in lakes, but also within the climate. It was a very warm winter and corresponded to the phase switch of the North Atlantic Oscillation and the Arctic Oscillation. And the 1998 period is also a really, that was actually the first year that this bay that we've been monitoring in Lake Superior since 1857 became ice-free. And many lakes started to become ice-free, and they had strong patterns in ice loss. And that corresponded to the El Nino Southern Oscillation and the Pacific Decadal Oscillation. I found this like really cool. So what we were able to notice in our ice records and our really long-term ice records. So the first panel here is from Torn River in Scandinavia, whose record goes back to 1693. This record is Lake Sua in the bottom panel. And both of these have a breakpoint here at different points corresponding to the industrial revolutions in the region. But what I just want you to notice is that before the breakpoint, there were both short-term oscillations and very long-term oscillations in these records. So this is a wavelet analysis, and I just want you to look at the red blobs with the black circles around them. You can see that there's, they're operating 16 to 48 years. Here's one that even extended past 64 years. But after the Industrial Revolution, these long-term oscillations are not so apparent in our data. And what we notice when we correspond this to the climate record is that there are these fundamental shifts in teleconnection patterns. For example, the North Atlantic Oscillation, if you read earlier textbooks, you would think of it as being a multi-decadal oscillation that's 20 to 50 years long. Now the 6 to 10 year period is much more influential since the mid-70s. Similarly, the El Nino Southern Oscillation, I thought that this was quite interesting. So back when the Shinto priests started recording the Amawatari, Enso was 50 to 60 years long. Now we're looking at a 2 to 8 year period. So these fundamental shifts in teleconnections also can correspond to extreme climatic events that may be further contributing to warming lakes. So we've done a lot of research on ice phenology because we have so much information that we've been able to gather. Recently, we're starting to look at ice thickness and ice quality. So this is actually my son who is out sampling with me at a local lake, and we were part of a Nguyen study looking at how ice quality has changes throughout the season in lakes around the world. And here we have thickness on the y-axis through different months of our lakes and the proportion of white ice. And this, I think, is the important consideration. So historically, we've had, when lakes freeze, cold temperatures, you get this black ice that's formed. A clear black ice that's actually allows for a lot of light attenuation, but also is stronger and structurally more stable. What we're finding now is that as winters are approaching like these warmer temperatures, we're shifting to more white ice conditions. So, for example, white ice may arise if you have temperatures that go from negative to positive Celsius above freezing, and you induce melting. If you have rain in the middle of winter. This winter is a perfect example of a situation where our lakes, if they have ice, are probably have a higher proportion of white ice. And white ice matters, and I'm going to talk about that in a little bit because it's a lot weaker than black ice. So you need it to be a lot thicker to be able to use the ice safely. And so that's what I'm going to head into talking a little bit about now. So ecologically, the implications of losing lake ice, and also culturally, what that means. So ecologically, I just mentioned in passing this changing ice quality affects light attenuation. So I'm not going to talk about this in this presentation, but I just wanted to raise it as something that we're looking at and many other researchers are looking at, is how changes in light attenuation can affect primary production under the ice in winter, and what we're seeing in terms of primary productivity. And there's a fantastic paper led by Stephanie Hampton, published in Ecology Letters in 2017 called Ecology Under Ice, that sort of sets the stage for some of the work that we're doing on under ice ecology. But first I want to talk about water temperatures. So this was a collaboration, fantastic collaboration, involving over 80 contributors. So we had people who were who observed water temperatures in situ. We worked with NASA to look at satellite temperatures as well, and also we had a group of modelers who modeled water temperature conditions. And what we did was we collected water temperatures for a 25-year period for over 350 lakes. And in yellow, what you can see are lakes that were collected in situ. So by people visiting the lakes, putting in, just measuring the water temperature throughout the summer months for a 25-year period. And you can see that they're mostly like situated in North America, Europe, and some in Australia. But large portions of the globe were missing. And so we teamed up with NASA who had also been recording water temperatures for the same 25-year period using satellites. And they were able to examine water temperatures in large lakes and in many regions that the limnologists that we know from Nguyen, for example, haven't been studying these lakes. And I think now these kinds of collaborations are more commonplace, but back in 2009 when we started the study, this wasn't something that was done often, which was kind of cool to be part of that project. And again, we made all this data available, open access. There's an R package, but you can also access the data from the scientific data paper. And what did we find? So we found that 90% of the world's lakes are warming. These lakes that we're studying, which represented actually more than half of the world's freshwater supply. And they're warming at a rate of 0.34 degrees Celsius per decade, which was faster than air temperatures and much faster than oceans. The other thing that we found was that ice-covered lakes are actually warming twice as fast. So their averages, I think, were about like 0.78 degrees Celsius per decade. So that was kind of interesting that ice-covered lakes losing ice cover are actually corresponding to warmer water temperatures. And we did a regression tree analysis here, and I'm not going to go into the details, but we found that ice cover was actually the most important variable, and we used this mean winter air temperature value to correspond to that. And then air temperatures and solar radiation were important factors as well, contributing to water temperature increases, as well as max depth. And I didn't show the plot here, but the next plot was actually a figure of all the lakes with these leaves. And I thought that was the most interesting thing, is that lakes not necessarily next to each other are warming in some similar ways. They might be, depending on some of their characteristics, but lakes in different regions in the world are have similar patterns if they experience similar climatic conditions. So it was a way to sort of get away from studying my lake or my lake my lakes in a small region, and kind of start getting at what are these global patterns and how are lakes behaving similarly, which was kind of cool. Oh, I guess I just wanted to mention there were 10% of these lakes were cooling. I didn't want to ignore that. In the Alps, for example, in Florida, those lakes were cooling for similar regions, that the land use changes had changed the water quality of those lakes that influenced their water temperatures. Whereas lakes in the Arctic and the Tibetan Plateau were also cooling because of melting glaciers, increasing, glaciers melting into these lake systems and putting cool water in this time period. So it's just kind of cool how different lakes in different regions may actually be more similar and behave more similarly than you might expect. And as the regression tree showed, the two most important factors contributing to warmer lakes that we found was again this air temperature link, very strong air temperature links. When air temperatures are warmer, water temperatures are warmer. And the second was solar brightening and dimming. So what's happened in the Northern Hemisphere is that because of improvements in air quality, we're actually seeing more solar radiation inputs in more recent years. And that brightening is contributing to water temperatures warming faster than you would expect just by climate change alone. And the Southern Hemisphere is actually becoming dimmer, contributing to lakes not warming as fast as you might expect. And here's just a summary from a review paper that Istin Woolway, John Small, and I recently wrote. But there's a lot of work that's done to get at this information. But basically, what we're seeing is because of shorter ice cover, earlier ice off, you have this longer open water period. Stratification of the lake, when the lake kind of forms these two layers, happens earlier, longer over the season, and it's also stronger. And that's corresponding to warmer water temperatures, higher evaporation rates. For example, in the winter, when you have less ice cover or no ice cover at all, that sort of lifts the lid on the lake, and we have higher evaporation rates that can contribute to water level changes, either decreases, but also there's a lot of precipitation changes that are happening as well that contribute to water level changes. Steve Jane published a great paper looking at how lakes are also experiencing, because of these increased water temperatures, declining oxygen levels at lower levels, deeper levels of the lake. And many studies have shown that warmer temperatures, changing precipitation patterns are contributing to increased primary production and increased prevalence of algal blooms, some of which may be toxic. And back during my PhD, and a few students of mine also work on fisheries to understand how warming water temperatures is increasing the habitat for non-native fish species, such as smallmouth bass, and decreasing thermal habitat for native fisheries like walleye or lake trout populations. And I'm just going to end talking about cultural and public health. And this is like a research direction that obviously is not where my training is, but I spend a lot of time trying to communicate the impacts of climate change on our freshwater systems to the public, and doing a lot of science communication and media outreach. And something that I noticed was that it's difficult to get people to relate to understand why this matters. And so unless you make it relevant to them. And so I've started doing some research in that area just to try to help engage that public discussion on climate change, to think about, well, climate change obviously has a dramatic influence on ecologically, but how do we get this to matter to people? And so so here we're trying to relate it to economics, because people care about money. But we're having some issues actually with this work, because we've documented, here you can see our projections with less ice cover, the annual economic loss, and the economic loss is in billions of dollars to local communities that rely on ice for skating tournaments or ice fishing tournaments, or just tourism in winter months. But there's some pushback, because if you're losing money because you have a shorter winter ice cover, you can make more money with a longer open water season. So there's some work that still needs to be done on understanding the economic loss of ice cover. We also have been looking at how warmer winters contributes to changes in cultural activities. So there's a skating race. So the skating race actually started in the Netherlands in the 1700s. And as like some of these countries have lost ice cover, the skating race keeps moving north. And now it's in Lake Mälaren in Sweden. And what you can see here is like, so here's the full skating race where you do it on across the entire lake. A loop is a shorter race, and then sometimes they have to cancel. And we can correlate this to winter air temperatures. So if the air temperatures are colder, we're finding that in colder air temperatures, you can do the full race. Whereas if temperatures are warmer, you may actually have to either do a shorter race or cancel the race altogether. And this brings, affects the community culturally, but also economically. Thinking about ice fishing, we went to Minnesota for some data on ice fishing. And an ice fishing tournament can bring in about $1 million of revenue to a small town in a weekend. So they're quite important. And here I just want to show you the relationship between ice fishing, between winter air temperatures and percent canceled tournaments. So as air temperatures approach even -2 degrees Celsius, we have this increased cancellations in ice fishing tournaments. We're thinking a lot about safety, ice safety as well. With warming temperatures, as I mentioned, there's less ice cover, there's thinner ice, and there's less high quality safe ice. And so one of those ways to think about ice safety is by the openings of winter ice roads. So this one, it's freezing degree days on the x-axis. So it's the opposite. So 200 would be a warm winter and 900 would be a very cold winter. And what we're noticing is a 3-week delay in ice road openings, which are really important. So winter ice roads connect remote many of them are indigenous communities, to access food, fuel, social networks in the winter. And so if the ice season is delayed, that delays getting access to critical supplies. If you think about, so here we've thought about like the duration of safe ice that you might experience, and we're seeing that although there will still be safe ice in the north, these southern latitudes that I showed you that are like sensitive to intermittent ice cover and are also warming at fast rates, even if the lakes still continue to freeze in these areas, they're not going to be safe for human use, even to skate on those lakes. And so this can be quite important for critical transportation infrastructure, such as snowmobiling, driving your car or pickup trucks to go ice fishing, and definitely transportation of winter ice roads and transport tech. So this is an area that we're spending a little more time on now to understand, like, what does this loss of ice mean for critical transportation and infrastructure, but then ultimately food security as well. And so what do we suggest? Well, here we've got total ice thickness and allowable load. That figure that I showed you earlier about when is ice safe to use, like 4 inches for a person to use it, 5 inches for snowmobiling. Those guidelines are based on an assumption that the whole ice core is made of black ice. And what we tried to show here is that we need this adaptation of those guidelines, because we're moving away from black ice conditions to more white ice conditions. And as you can see, if you have 10 centimeters black ice, you can hold 1,000 kilograms on the ice. But if it's white ice, it's only about 100 kilograms. And so that really dictates how safe the ice may be. And that corresponded to our next study looking at how many people are falling through ice and fatally drowning. And so here what I did was I contacted police stations and coroner's offices and life-saving societies, and we were able to put together a time series of winter drownings across 10 Northern Hemisphere countries. And what we found, again, here's winter air temperatures and the number of winter drownings per capita. What we found was this exponential relationship as you approach 0 degrees Celsius, where there are more winter drownings when winter air temperatures approach 0 degrees Celsius. There are a few exceptions. For example, Italy and Germany have very strong rules about when you can go out on the ice. And so there are fewer drownings because people follow those rules. And the other exception was Northern Canada, so the territories. And they had extremely high winter drownings per capita, even though the temperatures are so cold because of the high reliance on ice for hunting and fishing and travel. And not only do we observe higher winter drownings, there's also other studies that talk about the increase in the search and rescue events needed for these communities. So who's drowning? We wanted to get an idea of what people might be doing while they're drowning. And actually, this is like the saddest, I think, figure of all my research. If you're just playing on the ice, children under 9 comprise over 50% of the drowners. The other people who are most at risk are young people, particularly young males between the ages of 15 to 24, have been found to be at high risk for drowning when snowmobiling, for example. So it's really something that we need to talk about with the youth, just ice safety and being aware when you're outside, enjoying winter and ice activities. There isn't a magic solution. Everybody wants a magic solution to preserving ice cover. It really is dependent upon mitigating greenhouse gas emissions. As I showed you, if you have high greenhouse gas emissions, there's many lakes that could start becoming either intermittent or permanently lose ice within the century. But mitigating greenhouse gas emissions has direct implications for preserving our ice cover, but also the ecosystem function and cultural services that ice can provide. And so I'm going to end there. Again, thank you to all the great students and collaborators on this research, and I'm happy to take any questions.